Okay, we're going to pick up where we left off yesterday. So yesterday we went through uh, how we found the max and min, and then we found where it decreases on this interval, where it increases on this interval, and where it decreases again. So now that we've done that, we have to find inflection points. Remember that inflection points are the points where it switches from concave down to concave up. So we can only really estimate inflection points. And the way to do that would be to find the average in between the min and the max. So here we go from concave up to concave down, and then it stays concave down the rest of the way. So we only have one real inflection point, and that's where it switches here. So once I find my inflection point, I can then determine which interval it's concave up on and which interval it's concave down on. All right. So we found a max and min. Our min was at 0.087, and our max was at 1.913. And so all I have to do to find an estimate of my inflection point is to find the average of those two. So I just do 1.913, and I'm only looking at the x values here, plus 0.087, and then I divide that by 2. 1.193 plus 0.087 gives me 2, and 2 divided by 2 is 1. So my inflection point is going to be at 1, or right around 1. So now I have to find where it's concave up and where it's concave down. Concave up is going from negative infinity to 1. And I could do it like this as well. Negative infinity less than or equal to x, less than or equal to 1. I'd be fine with either way. And then it's concave down from 1 to infinity. So from here on, it's always going to be concave down, whereas before, concave up was from all the way back here to 1. So finding that inflection point helps us to find the intervals where it's concave up and concave down. And we got the inflection point from just finding the average of the max and min, the x values. So when I find that average, it's going to find me the halfway point between this minimum and this maximum here. Okay, graphing a piecewise defined function. So it says graph the piecewise defined function below. So for this one, I have two separate pieces that I have to graph. First one, excuse me, is x squared if x is less than or equal to 1. The second part of it is from 1 to 4. So if I look at this function, at the top part of it, I'm going to start at any number back here. So if I find negative 2, plug that in. Negative 2 squared is 4. So my first point, sorry, that was, should be negative 1 there. So my first point would be negative 2, 4. Then if I plug in negative 1 squared is 1. Plug in 0, it's 0. And plug in 1 again, that gives me 1. And so I can graph this using the points that I just drew. Obviously not perfectly. This one is going to have an arrow because it goes on forever to the left. whereas here it stops at 1. Because there's an equal sign under the inequality, I know that this is going to be a solid dot. Okay, the second part of the function picks up at 1 and goes to 4, but it does not include the point 1. In order to do this, though, I still plug 1 in. 1 plus 2 gives me 3. So when x is 1, that would give me 3. Because 1 is not included, you make an open dot. Now I can move on to my next point. 2 plus 2 gives me 4. And it would be 5. And then it would be 6. And because at 4, there's an equal sign under the inequality, that tells me that it's a closed dot. So that would be my graph. I don't actually need the points on it, just the line. I do need my endpoints though. So that's all we have to do is to graph the piecewise function. Look at our conditions first. Graph this part based on the conditions. This was where it was x is less than or equal to 1. And then graph the second part based on this condition. We can have piecewise functions that have a lot more pieces to them as well. Usually we'll go up to around 3, maybe 4, but never beyond that. Okay, this takes us to parametric graphing. In parametric graphing, the x-coordinate and the y-coordinate of each point on a graph are each given as a function of a third variable t, called a parameter. The functions that give the rules for the coordinates are called parametric equations. Then a parametric graph can be thought of as representing the function f of t, so a function of t, equals xy, and that's where x equals x of t and y equals y of t. So I have a parametric graph where my x is determined from a function of x from time, in this case, and y, where the y is a function. This will make a lot more sense once we get into the equations. So these are the rules that exist for our x and y coordinates that will go back in up here. The only time that we would use this is when we're talking about multiple things happening at once. If I'm looking at a function of time where I throw a ball, whenever I throw that ball, there's going to be some equation for how far I throw it and an equation for how high it went, or how high it is at a specific time. So that at any point in time, I could figure out how far the ball has gone. So like after 2 seconds, I could figure out how far the ball has gone into relation, like from where I'm standing, like did I throw it 60 yards, and how high the ball is off the ground. Parametric functions are the easiest and best way to solve questions like this. Okay, so let's graph a parametric equation. Graph the curve given by x equals 2t plus 1 and y equals t squared minus 3. So now we can choose values of t in order to come up with our equations here. So I have an equation 2t plus 1 for x, and y is t squared minus 3. So I'm just going to plug values in for t. 0, 1, 2, and I could actually do -2 and -1. and start with those values. Because we don't necessarily know that we're looking at time here. We just know we're looking at a third variable. Okay, so all I have to do now is plug these values in. X equals 2t plus 1. So 2 times negative 2, that's negative 4, plus 1 is negative 3. And I'll just keep going down this column. 2 times negative 1, negative 2 plus 1 is negative 1. 2 times 0 plus 1 is 1. If I can't tell, this is a linear equation because there's no exponent on the t, and it's going up by 2 each time, so I can proceed as I need to. For the y, it's t squared minus 3. So negative 2 squared is 4, minus 3 is 1. Plug negative 1 in. Negative 1 squared minus 3 is negative 2. Plug a 0 in. 0 minus 3 is negative 3. 1 minus 3 is negative 2. 2 squared is 4 minus 3, which is 1. And 3 squared is 9 minus 3, which is 6. Now, based off of these values, I have my new x and y. Negative 3, 1. Negative 1, negative 2. 1, negative 3. 3, negative 2. 5, 1. And 7, 6. Now I could just graph those points, and that would show me what my parametric equations give me. So there's going to be some times where I ask you to do it using this method. If you think about what we've done on Desmos so far, we've never done a parametric on this. So there's a way to actually do it. The way that we're going to do it is we're going to put it in parentheses as if we are graphing just points. And I'm going to put my equations in as x of t. So I can do x of t equals 2t plus 1, comma, and then y of t equals t squared minus 3. Well, well, well. Okay, so after I did this, if I take the x of t out and the y of t out and just put the equations in, that's going to give me my graph for my x and y values. You're also going to see this t showing up down here. I can set that to the intervals that I chose for t. Like I started at negative 2 and went up to 3. So if I put the lowest one and the highest one in, I can now look at my graph, and you're going to see that all these points show up. Now, it's not as nice as it is when we're graphing a normal equation, because it won't recognize, like when I click on it, usually it would bring up a point, but now it's not doing that. I don't know why, but I guess it is what it is. But this is the point negative 3, 1, just like we had. Additionally, we had the point negative 1, negative 2. So when I go over to negative 1, you're going to see that it's at negative 2. I think the next one was 1 and negative 3. You see that that point is true. What else do we have? 3, negative 2, 5, 1, and 7, 6. So if I go over to 3, that's at negative 2. 5 is at 1. And 7 is at 6. So when my x is 7, y is 6. And so we see that our graph matches up with what we found. All right, Monday we're going to get into our word problems involving parametric equations, and that'll finish this section up. Examples